Hello everyone. Today we are going to learn about linear regression model, how the algorithm works, uh, what values or what input value we provide, and behind the scene what happens, and what's actually the purpose. A little bit more in more detailed. Uh, so let me bring up my pen. And so here we have. Let's go from left to right. So here, at the very start of the process, we have to provide some input value. What are those values? They're basically the input value X and Y, which are the data, the data set. So we'll have to get when we're analyzing a problem, we'll have to get a lot of value where X is the independent variable and Y is the output, or X is the input and Y is the output. So we'll have to get this value, and that has to be quite a big data set. And we also have to provide W, or the which is the parameter, or also called weight. And number four, we'll also have to provide the form of a function which is called a hypothesis function. So what is actually a hypothesis function? So a hypothesis function is basically it's a function that predicts the ground truth, or the actual value of the output. So the whole purpose of linear regression is to predict the value of this y. Say we have some certain data of input and output, and eventually we would want to know what would be a unknown value of the output for a random value of input, which is not actually explicitly provided through this data set of X comma Y. So the hypothesis function that's why is a function that provides the prediction. So this function has two parts. The first part is called form, and the second part is called parameters. So what is the form of a hypothesis function? The form of a hypothesis function is how is the build of the function. For example, say we are trying to predict the value of y, but how we are trying to predict that really depends on us. Like what would be the kind of the pattern. So for example, for linear regression, these are some kind of problem. We are assuming that the value of X and Y should be linear, but there are also cases where for example, say uh, for mechanics, we know that the within the elasticity, the value of stress and strain is linear until a certain point. So for that certain point, we know that the material is gonna behave linearly. But there is also a non-linear region where it starts to behave non-linearly. So we'll have to basically have the understanding of how the physical system works, or how the physics actually work. So that is actually called the form. So that is something that the algorithm doesn't provide us. That is something that we'll have to provide it, and it is not gonna get improved. So this is what we provide, and this is what it takes, and it's gonna be eventually the form. So what actually the algorithm eventually provides us is a improved value of these parameters, which are represented by W. And this is not something that will have to provide like the exact value. For example, say if we had a problem where we know that as we were talking about the stress strain analysis. So say we know about the stress provided to a material, and there will be a strain, and we know that's within the elastic limit. So we surely know that the material behaves within the elastic limit. The material would behave in a linear way. But the question is, how linear, like, how would be the slope? So, and like the exact location of that linear plot. So that is something that we don't know. And if that is your situation, you can use this model. So, and that, like, how sloped the straight line would be is determined by W1 and W0, and this is kind of optimized through the algorithm. So this turns down to be a simple optimization problem eventually. So that's it. That's why we'll have to provide, a W, parameter, which is a vector, and that has all the elements of W1, W0, and if there were more values, components, say W2, W3, all of those would be under this vector. So this initial guess is eventually gets updated through the optimization process. And so this whole thing is called feedforward process. And then after we make this initial assumption of the y hat, which is the predicted value or the hypothesis function, it goes to this step where we calculate the difference between the actual value y and y hat. And the difference between this y hat kind of shows her how bad our guess was. Our guess could have been right bang on, like whatever is the exact value, but most of the case it wouldn't be. It's like actually almost all the case it wouldn't be, and it can be really close, but it wouldn't be the exact value. It depends on like how good prediction, how good guess was the value of W1 and W0. But that difference is accounted in terms of another function, which is called the cost function, also known as the objective function or the loss function. And this is yes, this is a function of y, the actual value of y and the predicted value of y, which is counting the difference between it. And there is a like derivation of the how it works, but I'm not going to that detail. Rather, I'm gonna give you the breakdown, a really useful breakdown of why head into like putting this value right here, w1 w1x minus w0. So this changes the cost function into a function of actually the weights or parameter which we want to optimize eventually. So here we basically, what we're trying to do is to find a relationship between the weights and the cost function. So we know that if we had a better prediction, if we can find better value of the weights, we would have lower value of j. But the question is, so that is one of the determining parameter how we would actually want to proceed towards optimizing the values of the weight. But yeah, so that's the thing. But there are some other more based on these assumptions. There are more mathematical detail that we will see, but not dig into the derivation again. Which will provide us the insight of how this is done. But this process of going back and coming up with new values of the weights and recalculating the hypothesis function and then recalculating the value of the cost function and seeing whether the value of j is lower than the previous iteration. So this is called the like feedback process, and like this turns out a gradient descent optimization process. So here we can see on the left in this box we have the conditions, as I was talking about, that the new values of the weight, the weight vector, is provided by actually based on the old value, like old iteration value, which we initially provided as a guess. And this is change, small change or big change depends on this value, which is called alpha. Alpha is known as the learning rate. This is something that we also have to provide as an input, and this is also a guess. And this portion is called the gradient of the cost function with respect to the weights. And here we have the equation. Again, we can see that the gradient is also a function of the weights, and eventually we want this to be zero. Like as the iterations goes, at one point we will see that we have come to a stable situation where stable values of the weights, where the old value and new values are nearly similar, and when this term is gonna be zero. And if this terms becomes zero, then one of the condition is the gradient would have to be zero. And this is basically the minimal optimization theory that we all know. So not gonna go to that details, because the main purpose of this tutorial is to going to the code, to the Python code that provides us the optimization of this problem. And also another thing is, so eventually when we'll get a stable value or value of the weights, then this will be the optimized value of W1 and W2, right? And when the W1 and W0 are optimized, or we have the best value, then the value of y hat would be extremely or very close to y, and that's our linear fit, and like the perfect linear fit, or like the best linear fit that we can get. And this would also mean that the value of j of the current iteration would be very like consistent with the previous one. That will turn to a like minimal value and would be constant, so the difference would be zero as well. So this would be a bit more clear if we see the graphs. So for example, so this is the initial, what I have explained, this is the initial situation where we have the x and y values. So the x and y, the actual values are this. These data points are the actual values, and so this is y. And we assume that this is going to be linear, and that's why we have predicted a form which is also linear or a straight line. And we have also guessed the value of the weights, which are W0 and W1, but the guess was terribly wrong. So that's why we can see that this one is y hat. Ultimately, when we calculate, we get this straight line, and there is a big gap between that. So there would be a big error. So this is counted in terms of, here we can see the initial iteration, we have a big J. The value of the cost function is significantly large. So here comes our machine learning, and like it becomes helpful here, where this J value is reduced, and with every iteration the value of the weights or the parameters gets improved, and this linear straight line actually changes its position based on the value of W1 and W0, the new values of W1 and W0. And this thing we will see like in a dynamic plotting when we will do the coding in the next lecture. But yeah, so in this process, as this straight line changes position, it would want to go to this direction or whatever. It would mainly want to minimize the error or the loss. So so here is the like I the values or the plots after more than 70 iterations. We can see it looks pretty good. It looks way better than previous. We can see that the data, the straight line goes through the data, and it kind of like shows like it kind of represents the value, and how much it represents we can also understand through this cost function. After 70 iteration, we can see like there is a constant value of j is like very much close to zero. The cost function's value is very much close to zero, and also we know that del j is equal to zero. So yeah, so that means that we have eventually reached to our situation. Another thing is important that we can see that it has we have kind of optimized our problem, and we know that we have found our hypothesis function, our finalized hypothesis function that can predict. And then say if we have a like random value of say anything that is not represented, say for example here in between this. So here we don't have any x or y data, but here we know what is the prediction. We know what would be for a value of x, what would be the value of y. So say for a value of strain, what would be the value of stress in terms of for our material stress strain analysis problem. So this thing we can easily find out like quite accurately through the when this is properly optimized. But another problem is like this. We can see that the value of j was just moving, like the iteration was carrying out, even though like it quite reached zero value here. Like I think like there was like 20 like 30 more iterations. The reason behind that, because this is there are still some del j is not actually exactly zero. It's very close to zero, but it's still trying to reach to the zero position. The question is, can it ever the value of cost function, so the difference, can it ever reach to a zero value? The answer is no. Like even if you can go to like millions of iterations, it's never gonna get to that zero value. Why? Because the machine, or like the machine you're running the software, there will be a certain precision which is called the machine precision, and this is finite, and therefore we'll have to provide a stopping criteria. So that is another thing. So we'll also have to provide a stopping criteria which is represented by epsilon. So, and we'll have to tell the program, okay, now stop. Say we want to stop the program when the error is, say, this. So when del j is, we consider del j is the error, and when this is this value, then the program stops automatically, because this is like quite precise, and we don't want it to be like very very precise. We'll also have to consider the computation time, and that means the cost, and also like equivalence to money. And so therefore, to summarize, for the whole process, we'll have to provide some parameter x, y, the actual values or the data set. We'll have to provide an initial guess. We'll very importantly have to provide the form of the hypothesis function. So this is something that where our knowledge of the problem or the physical system comes into play. We'll have to understand actually how the system actually works, whether it's linear or non-linear, or what kind of properties are it typically showing. So that is something that we'll have to first figure out and find out the form, and then we can actually come to this situation when we can run an algorithm. And then we also will have to provide the value of the learning rate, which is alpha, in the gradient descent optimization. And also, like, whether we don't want to go infinitely to with the program to solve this problem, so we'll have to stop the program when we are happy, and that is provided by epsilon, which is the stopping criteria. Thank you.